Non-examples of equal sets. So far we've been discussing what makes two sets equal. Now, we're going to switch gears and look at situations where two sets are not equal. This section will walk you through several examples to help solidify your understanding. It's really important to understand when sets aren't equal, because it's just as crucial as knowing when they are equal. Being able to identify differences is key to working with sets effectively. Now, let's quickly recall the core principle. For two sets to be considered equal, they absolutely must contain exactly the same elements. No more, no less. And this is the key point. If there's even a single element that's different between the two sets, then they are definitively not equal. We'll see this illustrated clearly in the examples coming up, so pay close attention to how even one differing element changes everything. In the next few slides, we'll look at specific examples to demonstrate this principle. Step 1. Recall the definition of equal sets. So we've just started looking at situations where sets aren't equal. But before we dive into those examples, let's quickly refresh our understanding of what it means for two sets to actually be equal. It's important to be solid on this foundation before we start identifying where things differ. Now, if we have two sets, let's call them A and B, we say that set A is equal to set B, and we write that as A equals B if and only if two things are true. Think of if and only if as meaning both conditions must be met, no exceptions. The first condition is that they must contain the same number of elements. If one set has 3 elements and the other has 5, they can't be equal, right? That's a quick check we can do right away. But just having the same number of elements isn't enough. The second condition is a bit more detailed. We need to make sure that every element that's in set A is also in set B, and every element that's in set B is also in set A. It's a two-way street. Essentially, if you were to list out all the elements of both sets, the lists would be identical, even if they're in a different order. We'll see how this plays out in the examples coming up, and how even a single difference will make the sets unequal. So, keep these two conditions in mind as we move forward. Step 2. Examining sets that are not equal. So now we're moving on to looking at examples of sets that aren't equal. Remember from the previous slides, we established that for two sets to be equal, they need to have the same number of elements and contain exactly the same elements. This slide will show us what happens when that isn't the case. Let's look at our first example. We'll define two sets, set A and set B. Set A, which we write as A equals the set containing 1, 2, and 3, contains the numbers 1, 2, and 3. And set B, B equals the set containing 1, 2, and 4, contains the numbers 1, 2, and 4. Now let's check if these sets are equal. First, we look at the number of elements. Both set A and set B have 3 elements. So, at first glance, the first condition for equality, having the same number of elements, seems to be satisfied. However, we need to check the second condition. Do they contain exactly the same elements? If we carefully compare, we see that set A contains the number 3, while set B contains the number 4. These are different elements. Because of this difference, even though they have the same number of elements, the sets A and B are not equal. We represent this mathematically by writing A is not equal to B. Keep this in mind as we move forward. Just having the same number of elements isn't enough. The elements themselves must be identical for the sets to be considered equal. We'll see more examples that build on this idea in the following slides. Example 2. Let's move on to our second example of sets that are not equal. As we discussed in the previous slides, remembering the definition of equal sets is key. Here we have two sets. We'll call the first set C, and it contains the elements B, C, and I'm writing that as C equals an opening curly brace, then B, C, and then a closing curly brace. Now let's look at set D. Set D contains the elements B and C. That's written as D equals an opening curly brace, a B, C, and a closing curly brace. The slide points out that we need to check the number of elements in each set. If the number of elements is different, we immediately know the sets aren't equal. Let's count. Set C has 4 elements, B, C, and set D, on the other hand, has only 3 elements, B and C. Because the number of elements in set C is different from the number of elements in set D, we can conclude that these two sets are not equal. We represent this mathematically by writing C is not equal to D. This example is pretty straightforward, and it reinforces the idea that having the same number of elements isn't enough to guarantee that two sets are equal. We also need to check if they contain the same elements, which we'll continue to practice in the following examples. Remember, in the next example, we'll see a case where the sets do have the same number of elements, but are they still equal? Let's find out. Example 3. Let's move on to our next example. On this slide, we have two sets. E and F. Set E is defined as containing the numbers 2, 4, 6, and 8. And set F contains the numbers 8, 6, 4, and 2. Now let's first check the number of elements. As you can see, both sets have 4 elements, so at first glance they might seem equal. But remember from the previous slides, simply having the same number of elements isn't enough to guarantee equality. This is where the element comparison comes in. If we carefully look at the elements within each set, we see that both sets contain exactly the same numbers: 2, 4, 6, and 8. Now, a crucial point here, and this is why this example is included, is that the order in which the elements are listed within a set doesn't matter. A set is defined by its members, not the way those members are arranged. So, whether we write 2, 4, 6, 8, or 8, 6, 4, 2, it represents the same set. Because both sets contain the same elements, we can confidently say that set E is equal to set F. We would write this as E equals F. This reinforces the idea that order doesn't affect set equality, and we need to focus on the elements themselves. Keep this in mind as we move forward, because sometimes students get tripped up thinking the order matters, but it absolutely does not when dealing with sets. We'll continue to build on this understanding in the following examples, and we'll also look at some common mistakes to avoid. Example 4. Let's move on to our next example, which is a bit of a trick one. On this slide, we have two sets. G and H. Set G is defined as containing the elements 1, 2, 2, and 3. And set H contains the elements 1, 2, and 3. Now, when you first look at these, you might quickly think they have different numbers of elements and therefore aren't equal. It appears like both sets have 3 elements. However, and this is a really important point about sets, sets only list unique elements. That means we don't repeat elements within a set. So, if we write out set G, properly representing a set, we remove the duplicate 2. This means that set G is actually equivalent to the set containing 1, 2, and 3, just like set H. Now let's compare. Both sets, G and H, now contain exactly the same elements, 1, 2, and 3. Because of this, we can confidently say that set G is equal to set H, which we write as G equals H. This example is crucial because it reinforces that when comparing sets, we don't count repeated elements. We only care about the distinct or unique elements present in each set. Remember this, as it's a common mistake students make when determining set equality. We'll be building on this understanding as we move forward, so make sure you grasp this concept. Step 3. Identifying the key difference. Let's solidify what we've been learning about equal sets. This slide really drives home the most important idea. The crucial point to remember is that for two sets to be equal, they must have exactly the same elements. Think of it like a perfect match. If you're comparing two sets, every single thing inside one set needs to be found inside the other, and vice versa. There can't be anything extra or missing. And this next point is a direct consequence of that. Any difference in elements, even a single one, means the sets are not equal. So, let's say we had two sets, and they both had most of the same numbers, but one had an extra number the other didn't. Immediately, those sets are not equal. We'd use the not equal to symbol, which looks like an equals sign with a slash through it, to show that. Remember back to example 1, where we had A equals 1, 2, 3 and B equals 1, 2, 4. Both had 3 elements, but because of that difference, 3 versus 4, we knew A was not equal to B. This slide is just reinforcing that principle. Keep this in mind as we move forward, because it's easy to get caught up in just counting the number of elements, as we'll see on the next slide. But remember, The elements themselves are what truly determine if two sets are equal. Common mistakes. Let's move on to this next slide. It's about spotting some common pitfalls when determining if sets are equal. A common mistake is to focus solely on the number of elements. Now, remember back to our definition of equal sets. We said that two sets need to have the same number of elements and contain the exact same elements. It's really easy to get caught up in just counting how many things are in each set. But as we've seen in the examples, just having the same count isn't enough to guarantee equality. While the number of elements must be the same for sets to be equal, it's not enough on its own. This is reinforcing that point. Think of it like a checklist. Having the same number of elements is the first thing to check, but it's not the only thing. If the counts don't match, you immediately know the sets aren't equal, like we saw with sets C and D, but if the counts do match, you're not done yet. You must also verify that each element in one set is present in the other. This is the crucial second step. You need to meticulously go through each element in the first set and confirm it's also in the second set, and then do the same in reverse. If even one element is missing from either side, the sets are not equal. Remember example 1, where A contained 3 but B contained 4, they had the same number of elements, but weren't equal because of what those elements were. So, this slide is a really important reminder to be thorough. Don't let the initial count trick you into thinking sets are equal when they're not. We'll wrap things up with a quick summary on the next slide, solidifying these key takeaways. Key takeaways. Let's wrap up our discussion on non-equal sets with these key takeaways. This slide summarizes what we've learned. The first point states that two sets, which we can generally refer to as A and B, are considered not equal, and we write that as a not equal to B if they do not contain exactly the same elements. Remember, equality is strict. Every single element must match for the sets to be considered the same. The next point is really important and a common area where students make mistakes. It says that even if two sets have the same number of elements, they aren't necessarily equal. We saw this in a few of our examples. Just because both sets have, say, 3 items doesn't automatically mean they're the same set. You must check the actual elements themselves. Finally, and we touched on this with example 4, remember to consider only the unique elements when comparing sets. Sets don't allow for duplicates. So, if a set lists an element multiple times, we only count it once when determining equality. This is crucial to avoid misinterpreting the contents of a set. So, keep these 3 points in mind as you practice identifying equal and non-equal sets. This will help you avoid common pitfalls and build a solid understanding of set theory. Are there any questions about these key takeaways before we move on?